Hello, my name is Jinseok Choi. I'm an assistant professor at electrical engineering, KAIST. Today I'm going to introduce my research work for the road toward 6G communications in terms of energy efficient communication view. Before starting with my research, let me briefly introduce myself. My name is Jinseok Choi. I had a PhD degree from the University of Texas at Austin, and I worked at Qualcomm, UNIST before joining KAIST. In the first chapter, let me overview my research work in terms of the 6G requirement and the research topics. 6G communication has various requirements to be a key communication network. And here are some key enablers as well. So first, 6G communication needs a very high data rate, efficiency, and very low latency, high coverage, and high reliability, and so on. So to enable and to achieve those requirements, we need those following research aspects: bandwidth, antennas, hardware, multiple access techniques, and new frame structure, and new network. So in my research, I'm investigating most of these dimensions to enable these 6G communications so that I can increase the data rate and energy efficiency, spectral efficiency, and also increase the reliability while decreasing the latency of the communications. Also recently, I'm also working on increasing the security of the wireless communication and also increasing the coverage. So here are a brief history of my research from past decade. So from 4G, I started studying MIMO communication, which is called multiple input, multiple output communications. So I performed some network analysis to find out what's the upper bound of our network can do. And with the advent of millimeter wave communications, which uses very high frequency range to exploit large bandwidth, and also the advent of massive MIMO communications, I try to develop a transceiver design which uses very low power but achieve very high channel capacity. And in terms of the millimeter wave communications, I used a channel sparsity, which is a key feature of the millimeter wave. And for massive MIMO communications, a low power hardware is especially introduced. And nowadays, physical layer security has been very famous to enable these low computing device communications such as IoT. So my work includes security and short packet transmission for ultra reliable low latency communications. And the satellite communication has been also investigated in my research to find out the true network coverage of the satellite communication systems. So I'm still working on very hard to enable the 6G communications in terms of the physical layer perspective. So in this talk, let me introduce my key research achievement in energy efficient communication systems, especially for the uplink and downlink communications. So today, the key challenge of the wireless communication is the power consumption. The reason why the power consumption is the key challenge is as follows. We have two basic network trends. First, antenna massification. Second, bandwidth massifications. So antenna massification means using lots of antennas. And bandwidth massification means we use very wide bandwidth compared to the current bandwidth. In this regard, the power consumption issue happens at the base station as well, because the very power demanding devices and circuits such as analog to digital converter increases with the number of antennas and also increases with the bandwidth. So as you can see on the figure on the bottom right, the millimeter wave communications and terahertz communication can further increase the power consumption of the ADC devices. Therefore, the ADC uses significant power, which is not affordable for most vendors. So I believe there is no 6G without handling such power consumption issue. So as a solution, we can decrease the number of bits so that we can exponentially decrease the power consumption at the ADC. However, decreasing the resolution of ADC means we will introduce additional quantization error. So as you see here, the quantization error is a key bottleneck of the spectral efficiency, or also known as the data rate. So without any quantization error that means the quantization bit is considered to be infinite. We have no upper bound and saturation point on the graph. However, if we decrease the number of bits, we can easily observe the very decreasing trend of the spectral efficiency with decreasing number of bits. This is because the quantization error also increases with the signal power, so it can be a main bottleneck of increasing the signal quality, called SNR or SQNR. So we have to efficiently deal with the loss of the quantization. So I proposed two-stage analog bit combining receiver in the umlink directions to manage such quantization error behavior in a minimal perspective. Before starting with my proposition, let me briefly overview the history of the beamforming. We have 4G, 5G, and 6G beamformers. And in 4G, the beamforming is mostly done in the digital domain. Because there are a few antennas at the devices, the digital beamforming can be very efficient and very easy to handle the processing. However, as the number of antennas increases for 5G, we need to add some additional networks called analog combiner, so that we can reduce the number of RF chains which contains power demanding circuits while maintaining the same number of massive antennas. So by introducing such analog circuits, we can reduce the power demanding RF chains, but can achieve high channel gain from the most of the antennas. So it's a possible low power solution for massive MIMO communications. But nowadays, with the massive number of antennas and with massive bandwidth, 6G beamforming requires additional power saving. So for example, we may need this analog combiner and also the low resolution ADCs at the same time. So we can have the more flexibility in reducing both the number of RF chains and the quantization bits. However, this existing strategy for the hybrid beamforming cannot be directly applied to the 6G beamforming structure because the quantization is introduced and it's a function of the analog combiner. So we have to carefully design this analog combiner to deal with the quantization distortion. So this is my main focus, and I'll show you why the conventional approach is not really applicable. The conventional approach with the analog beamformer or just a digital beamformer is to maximize the channel gain when received signals from the various antennas. Once the channel gains are collected, the channel gains are unevenly distributed over different RF chains, which is in small dimension. Then, for some RF chains will has very significant quantization error. Here are some examples at the bottom. So when we have no quantization error, as I mentioned, maximizing the channel gain is the proper strategy, an optimal strategy. So some beamformer can be applied in front and then collect most of the channel gain onto the lower dimension, but those collected channel gains can be uneven distribution. However, this uneven distribution doesn't matter if ADC doesn't introduce any quantization error. However, as you see in the middle, we have the same beamformer which collects most of the channel power and has different power distribution on the ADCs. Then with the low resolution ADCs, the significant quantization error happens for the ADC with large channel gain. but the quantization error is very small for the ADC with small channel gain. And this is a very inefficient way of quantizing the signal with the given same bits. So it's not very optimal. So my insight is to introduce some analog beamformer which maximize the gain, but also evenly distribute the collected channel gain over the available RF chains, so that ADCs with same bit can give similar level of the quantization error. So this is the desirable behavior of the analog combiner plus the low resolution ADCs. Inspired by this insight, I found out that we have two-stage analog combiner, and it's actually quasi-optimal. So we need two-stage combiners. First stage, as you see in the bottom, collects the most of the signals onto the lower dimension, just like the conventional approach. So this collected signal has different and uneven distributions over the RF chains. Then we need the second stage analog combiner, which is called unitary matrix, and DFT matrix can be one example. So this second combiner distributes these collected signals over all the RF chains evenly. So if you see the graph on the right side, you can see that the red curves from the two-stage analog combining shows very even channel gain distribution over all RF chains. However, this one-stage combining case shows very uneven distribution, which gives a significant penalty when the quantization happened. So I plot the performance of my two-stage combining analysis with my previous work, resolution adaptive ADC. So they are basically the complement to each other. The two-stage analog combining case has the fixed ADC bits, and it tries to optimize the inputs for the ADCs. However, the resolution adaptive ADCs has variable resolutions of ADCs, and we have kind of fixed conventional combiners at the front. So given these signal gains after the combiner, the ADCs will adaptively change its resolution so that it can have very efficient quantization. So you see the curves of the SE, the signal spectral efficiency versus the energy efficiency trade-off, and I plot for a different number of RF chains, 20, 16, 12. So the black curve and the red curves are the proposed method, and the blue is the conventional method, and the green is just fully digital case without using any hybrid approach. So as you can see that as the number of ADC bits increases, the spectral efficiency and the energy efficiency both increases at a certain point. And when beyond some ADC bits, like 6 bits, the spectral efficiency keeps increasing while the energy efficiency started decreasing. So there are some optimal points, and our approach can expand this optimal point and the range of the trade-off, and also achieve the higher trade-off between the spectral efficiency and the energy efficiency. So in summary, our proposed method has the highest performance in terms of both the energy efficiency and the spectral efficiency compared to the conventional approach, and the fully digital case, which doesn't use this hybrid approach, has very limited trade-off region. So our proposed method is a very promising 6G beamforming architecture. So far I've been talking about the uplink solution. So now let me focus on the downlink case with the quantization as well. So let me start, before starting the detailed examples and explanations, let me briefly overview the history of multiple access techniques. So we have 4G multiple access, which is called spatial division multiple access SDMA. So in this case, with multiple antennas, the base stations nullify and orthogonalize the users within the signal space dimension. So when we have enough spatial degree of freedom, means enough antennas, we can orthogonalize the signals for each user so they don't have any interference from each other. This approach is very easy to perform, but when the number of antennas is small, the users and the number of users is larger than the antennas, then that becomes the overloaded system, and this cannot deal with such overloaded case. So in 5G multiple access, the NOMA has been introduced, called non-orthogonal multiple access. So when this overloaded system happens, the NOMA can effectively cancel the interference so that the sum rate can be maximized. The principle of the NOMA is as follows. We have the two users, for example, and we are going to use the same time, space, and frequency dimension. So their symbols are superpositioned and transmitted. Then the user one, who is called strong user, which has better channel quality, decode the user channel symbol first and cancel it through the signal successive interference cancellation. Then when decoding its own signal, W1, it doesn't have any interference. But for the user 2, which is called weak user, we'll just have to decode its own signal without canceling the user 1's signal. So it has interference. But in the sum rate, it's optimal. But this is very sensitive technique to the decoding order. So we have to, every time we have to find out who's the strong user and who's the weak user. For some simple case, when antenna is one and there are two users, it's very easy to compute the channel gain, and the ordering is very straightforward. However, if we have more antennas and many users, this problem is very, very, very hard to solve. So this is not really practical for some complicated scenario. So for 6G case, new types of multiple access has been introduced, and this is the one example. So rate splitting multiple access is bridging the gap between the SDMA and the NOMA. So rate splitting also has two types of signals, user 1 and user 2, for example. Then user 1 introduces its private message and also its common message. User 2 also introduces its common message and private message. Then those common messages from each user are combined and encoded for the one general common message, which can be decodable at both users. So once those users receive their signals, they first decode the common message and they takes their own part and then cancel the WC, the common message. So when decoding their private message, they don't have any interference from the common message, which results in the reduced interference from each other. So it's also good to handle the overloaded system. And it's practical because there's no need for the ordering of the users. So rate split multiple access, RSMA, has been introduced in the past and now extended to the broadcast channel, and it's called a quasi-optimal transmission method. So when the interference strength is weak, the RS is also optimal with other SDMA method. However, when the interference increases, RSMA still optimal, but the SDMA is not optimal, and the NOMA types of strategy is optimal. So the RSMA is adaptable to the interference strength and very robust in performance. So it's optimal for any regions. So it's bridging the gap between the SDMA and the NOMA method. So here's the reason why I first introduced this RSMA method. So here's a significant role for the RSMA in low resolution quantization system. So let's assume we have the antennas with low digital to analog converter and high resolution digital to analog converter. Then when we have low SNR, like low signal power, they transmit the same, almost similar transmit power for both the low power, low DAC antenna and high DAC antenna. Because the quantization error does not really matter, because signal power is very low compared to the noise power, so it's still okay. However, in high SNR, when the signal power is very good compared to the noise power, using the low resolution DAC means introducing significant quantization error, which becomes a very significant noise. So the transmitter does not want to use such antenna. So it only puts most of the energy and power to the antenna with the high resolution DAC. Therefore, in this case, we may turn off some antennas when transmitting the signals. Then, when the number of users is larger than this active antennas, this becomes the overloaded system. So in this case, it has very strong interference. So the conventional SDMA approach does not work. So the RSMA can handle this situation as well. So RSMA can play a key role in managing the quantization error and also the interference. So it has very large synergy with the quantization system. So based on this insight, I proposed use the RSMA systems and develop some optimal pre-coding method to minimize quantization error while maximizing the sum rate. So the sum rate maximization has two parts, the common rate and the private rate, subject to the transmit power. The solution is found at the base stationary point by using the proposed method. So that means it can be one of the best local optimal solution. So by developing such RSMA-based pre-coding method for the quantized system, for the mixed DACs, I plot the sum rate versus the signal power. Then as you see on the left curve, the proposed method has the highest sum rate over the most of the SNR range. And compared to the SDMA, we can have a dramatic increase or noticeable increase when using the RSMA. So this RSMA gain comes from efficiently use the antennas and handling the interference. So for example, if you see the antenna power, for the RSMA case, when the signal power is weak, we have a large portion of the signal power at the low DACs, but antennas with high DACs has the power increasing when SNR increases. And the antennas with low resolution DACs is almost turned off when SNR is very high. So that means it can become a low overloaded system because the number of active antenna is small. In this case, the RSMA can effectively and efficiently handle this overloaded system by introducing more common rate. However, for the conventional SDMA case, this low resolution DAC is still active when the SNR is very high. So that means it still works, but it's introducing a significant quantization error compared to the noise level, so which is not very desirable. So such limitations have this gap between the RSMA case and the SDMA case in the sum rate. So last curve shows the split view of the common rate and the private rate. So in red, we have the private rate in straight line with the circles, and the dotted line means the common rate. So as the SNR increases, like the signal power increases, the private rate started decrease at some point, because at this point, we're going to reduce the number of active antennas to avoid high quantization error. But the common rate increases since it can deal with this overloaded system. So the overall sum rate is higher than the SDMA. So this RSMA is very suitable solution for this low power system, and we optimize this RSMA based quantization system processing. So in conclusion, our goal was to optimize the communication efficiency in terms of both the spectral efficiency and the energy efficiency. And the key challenge, such power consumption, is managed by using the 6G beamforming architecture and 6G multiple access architecture. So our proposed method enhance the spectral efficiency and also provided very low power design for the base station. So in terms of the 6G KPI, we have fulfilling many 6G key requirements, including data rate, energy efficiency, spectral efficiency, and the peak data rate. Thank you for your attention. This is the end of my presentations.